Industrial controllers. Hello everyone, my name is Rafael. I'm an electrical engineer, and in this video I would like to invite you for a conversation about industrial controllers. And to do so, I'm going to present to you some concepts related to automatic control and solve 3 exercises. Let's go do it. Automatic controllers. An automatic controller compares the actual value of the plant output with the reference input, determines the deviation, and produces a signal that will reduce the deviation to 0. This is the control action. Take a look at the figure on the board. The figure shows a block diagram of an industrial control system. Now let's consider the different types of control actions. Number 1, two position or on-off control action. The actuating element has only 2 fixed positions, on and off. On-off control is simple and inexpensive and widely used in industrial and domestic control systems. If U of T is the output signal, from the controller, and E of T is the actuating error signal, we're going to have 2 possibilities of output. U of T equal to U1 of T when the error signal is greater than 0, and U2 for E of T less than 0. Okay? The error signal is here. When the error signal is greater than 0, we have 1 possibility of output. When the error signal is less than 0, we have the other possibility of output, where U1 and U2 are constant. 2-position controllers are generally electrical devices. One example is a solenoid-operated electric valve used in such controllers. Solenoid-operated electric valves. Now let's see the other. Number 2. Proportional control action. Proportional control action. Proportional control action. For a controller with proportional control action, the relationship between the output of the controller U of T and the actuating error signal E of T is U of T is the output and E of T is the actuating error signal, is equal to Kp times E of T. Okay? Where Kp is the proportional proportional gain. In the frequency domain, US over E of S is equal to Kp. Okay? This is the proportional control action. The proportional controller is essentially an amplifier with an adjustable gain. Now let's consider the integral control action. Integral control action. Number 3 now. Number 3. Integral control action. In a controller with integral control action, the value of the controlled output, U of t, is changed at a rate proportional to the actuating error signal E of t. Okay? Remember that U of t is the output and E of t is the actuating error signal. That is, for the integral control action, the derivative with respect to time of the output is equal to Ki times E of t. Okay? Which can be rewritten as U of t is equal to Ki times the integral from 0 to t E of t dt, where Ki is the integral gain. And the transfer function in the complex domain is U of S over E of S equal to Ki over S. Okay? This is the integral control action. Now, let's combine the proportional with the integral control actions. And we're going to study now the proportional plus integral control action. Number 4, proportional plus integral control action. We are calling here PI control action. We're going to combine the possibilities provided by the proportional control action with those of the integral control action. The control action of a proportional plus integral controller is defined by the equation: the output U of t will be equal to Kp E of t, this is the proportional, plus Kp over Ti times the integral from 0 to t E of t dt, and this is the integral. Okay? We are combining the proportional action with the integral action. And in the frequency domain, it becomes u of t, u of s, over e of s equal to kp 1 plus 1 over ti times s. Ti times s. Okay? This is the transfer function for the PI control action. Where ti, this term here, ti, is called the integral time. Ti is the integral time. Okay, now let's consider the derivative action. Number 5, PD control action. Proportional plus derivative control action. The control action of a proportional plus derivative controller is defined by the following equation. The output is related to the actuating error signal by Kp E of t, this is the proportional, plus Kp times Td times the derivative with respect to time of E of t. And this is the derivative. Okay? We are combining the proportional control action with the derivative control action. And in the frequency domain, the transfer function becomes u of s over E of s equal to Kp times 1 plus Td times s, where Td is the derivative time. Okay, now the last one is the PID control action, proportional plus integral plus derivative control action. Let's see how it is. Number 6, PID control action. PID control action. Proportional plus integral plus derivative control action. This combined action has the advantages of each of the three individual control actions. The equation of a controller with this combined action is given by, okay, the output u of t will be equal to Kp E of t, this is the proportional action, plus Kp over Ti times the integral from 0 to t E of t dt, this is the integral action, plus Kp times Td times the derivative with respect to time of E of t. This is the derivative control action, and in the frequency domain, the transfer function becomes U of S over E of S is equal to Kp times 1 plus 1 over Ti times S plus Td times S. Okay? Where Ti is the integral time, Td the derivative time, and Kp the proportional gain. The block diagram of a PID controller is, okay, let's draw the block diagram of a PID controller. Okay, after this, we draw the block diagram of a PID controller. We have here Kp 1 plus TIS plus TI TD S squared, it all divided by TIS. Here the output in the frequency domain. Here the error detector, the feedback branch, the error signal here, and here the reference. And this is the block diagram of a PID controller. There may be some things here, there may be other things here, but the controller is this. You can have the plant here in this side, the plant that you want to control, but the PID controller is basically this. Okay, now let's understand more deeply each one of the control actions. Let's consider PI control again. In the proportional control of a plant whose transfer function does not possess an integrator, there is a steady-state error or offset in the response to a step input. Let's demonstrate why it happens and how to fix this problem. Letter A, proportional control. This is a PI. This is the proportional control. Okay, only the proportional control here. And G of S is equal to K over TS plus 1. This is the plant. We wish to control it only by adjusting the gain. And let's see what happens. We're going to discover that there will be an error or an offset to a step input. And since E of S over R of S is equal to R of S minus C of S over R of S, which is equal to 1 over 1 plus G of S, the error, okay, the actuating error signal is going to be E of S equal to R of S 1 plus G of S, which is equal to R of S 1 plus K TS plus 1. Okay? For a unit step input, R of S is equal to 1 over S. We have that E of S is equal to TS plus 1 over TS plus 1 plus K, 1 of S. And the steady state error is then going to be ESS is equal to the limit S going to 0 of SE of S equal to 1 over K plus 1. What does it mean? It means that there is going to be a steady state error of this magnitude C of T, T, and here the output. And this is the offset. This is the steady state error to a unit step input. Okay, if we choose to control the plant only by adjusting the gain, we're gonna have a steady state error here. How can we fix this problem? We can fix this problem by using an integrator. When we use an integrator, in series here, or in parallel, depending on how you choose to use, you're going to be able to reduce this steady state error to 0. Now let's analyze the integral control, which is going to be letter B here, and how to reduce this error, because we want to compare the output signal with the reference input. When the reference input is the unit step input, we wish the output to be equal to 1. Okay? But if there is an error, the system is never going to be fully controlled. We need an integrator to be able to reduce the control action, the actuating error signal to 0. Okay? So the system will reach steady state. Letter B, integral control. Now, instead of K here, we're going to have K over S. Okay? The closed loop transfer function of this block diagram is going to be C of S over R of S, which is equal to K S TS plus 1 plus K. And the error signal E of S over the reference input is going to be R of S minus C of S over R of S, which is equal to S TS plus 1 over S TS plus 1 plus K. Okay? The steady state error is reduced to 0. The steady state error is equal to the limit when S goes to 0 of SE of S, and in this case it is 0. We're gonna see that this is what we wish. We wish to use the integral control to reduce the steady state error to 0. Now, let's see how it happens when we have disturbances, any kind of stochastic, any kind of random disturbance. Okay, let's do it. Let's study disturbances and see how they impact our control action. Any kind of system, it can be a furnace, it can be a damping system. We can always have disturbances, and we are going to study how these disturbances affect our control action. Okay, we're gonna have an error detector here, the reference here, here. At first, we're going to use the proportional controller only and see what happens if we need or not to add to this the integral controller. Here, you're gonna have the error detector again, and here S JS plus B, and here our disturbance. The output okay, we're gonna have a disturbance D, and we want to assess how this disturbance affects the control action. It's then our letter A, the proportional control. Okay? Let's investigate the effect of a torque disturbance occurring at the load element. Consider the system of the figure, okay? This is the proportional controller. This is the disturbance. The disturbance is represented here by a torque disturbance on a motor, for example, a torque disturbance on a motor, a servo motor, for example, and this is the representation of the plant, the motor. The proportional controller delivers a torque T to position the load element, which consists of a moment of inertia and viscous friction. This is the representation of an electric motor. An electric motor consists of a moment of inertia and a viscous friction. Torque disturbance is denoted by D. Assuming that the reference input is 0, at first, you're going to assume that R of S is 0. We're going to assume that R of S is 0. The transfer function between the output and the disturbance D of S is given by since C of S over R of S is equal to 1 JS squared plus BS plus KP, the error signal E of S over D of S is equal to the negative of C of S over D of S, which is equal to the negative of 1 over JS squared plus BS plus KP. The steady state error due to a step disturbance torque of magnitude TD is the steady state error is equal to the limit S going to 0, S E of S, which is equal to the negative of TD over KP. What does it mean? What does it represent? The steady state error due to a step disturbance of magnitude TD is this, the negative of TD over KP. At steady state, the proportional controller provides the torque negative TD. Negative TD is the controller provides a torque equal to negative TD, okay? And the disturbance here acts with a torque TD, and the controller will provide a torque equal to negative TD, the opposite of the disturbance. The steady state output due to the disturbance is the output in steady state is equal to the negative of the error signal, which is equal to TD over KP. Okay. And how can we profit from this? If KP is large, the torque disturbance can be made quite small, can be reduced to almost 0, okay? If we have a disturbance represented by TD, which is the torque due to the disturbance, if KP, the proportional gain, is very large, then this disturbance will not affect much the motor that we are controlling. Now let's insert an integral controller there and see how we can improve the system and make this less vulnerable to any kind of disturbance. It's gonna be letter B. Letter B is gonna be PID Control, and let's observe what's happening when a disturbance occurs in a system controlled by a PID control. To eliminate offset due to torque disturbance, the proportional controller may be replaced by a proportional plus integral controller if integral control action is added to the controller. Then, as long as there is an error signal, a torque is developed by the controller to reduce this error. Okay? This is what the integral action does. It reduces the steady state error. Okay, and the figure is going to be changed. Instead of only Kp here, we're going to have Kp 1 plus 1 over Ti S. Okay? This is the transfer function of the PID controller. The closed loop transfer function between C of S and D of S is going to then become C of S. Observe that here is Kp 1 plus 1 over Ti S. And the closed loop transfer function is of the sort ds, which is equal to S js cubed plus bs squared plus kp s plus kp over ti. This is the closed loop transfer function. As we are analyzing only the disturbance and not the input, we are going to make R of S equal to 0. R of S is going to be set to 0 to analyze only the disturbance, the effect of the occurrence of a disturbance. The error signal is going to therefore be E of S is equal to the negative of S j s cubed plus bs squared plus kps plus kp over ti. Okay? This is and multiplied by the disturbance. The steady state error is going to then be reduced to 0. We're going to conclude that E as S is equal to the limit of S going to infinity as E of S equal to 0. Again, we are stressing that the addition of the integral control action causes the steady state error to be reduced to 0. Now let's analyze the derivative control action. We have already analyzed the integral control action in combination with the proportional control action. Now let's see the combination of the proportional action with the derivative action. Derivative control action. Derivative control action, when added to a proportional controller, provides a means of obtaining a controller with high sensitivity. Okay? So these are the benefits of combining the integral action and the derivative action to the proportional action. The integral control action reduces the steady state to 0, okay, causing thus the system to have a moment of rest. Otherwise, the control action will be going on forever without ever achieving steady state. And the derivative control action provides more sensitivity to the system. Okay? An advantage of using derivative control is that it responds to the rate of change of the actuating error and can produce a significant correction before the magnitude of the actuating error becomes too large. Okay? Then, to prevent the actuating error signal to become too large, we may use a derivative control action. Then the derivative control action anticipates the actuating error, initiates an early corrective action, and increases the stability of the system. Now let's observe the proportional control of a system with an inertial load. We are going to study what happens when we use only the proportional controller, and after that we are going to use the derivative control action to see how the system is improved by the addition of the derivative control action. Here we're going to have the proportional control only, letter A, proportional control. Okay? We are comparing the proportional control with the derivative control and see how the derivative control can make the process improved. How we can improve control action by the addition of a derivative controller. Okay, we're gonna have again here the proportional controller, okay, only an adjustable amplifier. Here, the plant, okay, the plant here is a system with an inertial load only. This is the output, this is the error detector or the error, if you prefer, you can call it the error or the error detector. Here the feedback loop. And this is it, okay? The closed loop transfer function of the system is going to be C of S over R of S is equal to Kp over Js squared plus Kp. Okay, this is the closed loop transfer function of this feedback system. And the output, okay, since the roots of the characteristic equation is the denominator of that closed loop transfer function. Since the roots of the characteristic equation are imaginary numbers, if you carry out this algebraic manipulation and discover the roots of the characteristic equation, you're going to see that they are imaginary numbers, and the response to unit step input oscillates indefinitely. Okay? If R of S is the step, then the output, we have one here, the output is going to oscillate forever. Forever. How we can reduce this? How we can control the transient period of the output? We are going to use a derivative control action, or if you prefer, a PID controller, a proportional pulse derivative controller, to eliminate this forever going oscillation. Let's observe the purpose of a proportional plus derivative controller. The derivative control is essentially anticipatory, measures the instantaneous air velocity, and predicts the large overshoot ahead of time, and produces an appropriate counteraction before too large an overshoot occurs. Consider the system of the figure. The closed loop transfer function is given by C of S over R of S is equal to Kp 1 plus TdS over Js squared plus Kp TdS plus Kp. This is the closed loop transfer function of the system of the figure. The characteristic equation is the denominator of that equation. The characteristic equation Js squared plus Kp TdS plus Kp equal to 0 has two roots with negative real parts for positive values of J, Kp, and Td. Thus, the derivative control induces a damping effect Observe the following image. Without the derivative controller, we had forever going oscillations. Now, the system is damped. There will be oscillations, but the system will reach steady state at the reference value of 1. And this is how we can improve the system using derivative control. The response curve shows a marked improvement over the original one, where oscillations continued on forever. Now let us see. We are going to assess proportional plus derivative control of a second order system. The first was a first order system. Now we're going to do the same for a second order system. Let's do it. We're going to change here and control a second order system. We're going to control a second order system. A compromise between acceptable transient response behavior and acceptable steady state behavior may be achieved by use of a proportional plus derivative control action. Consider the system of the figure. The first one, letter B, was a first order system. Now, letter C, we are controlling a second order system. The closed loop transfer function of the system is of the sort C of S over R of S is going to be equal to Kp plus KdS over Js squared plus B plus Kd S plus Kp. Okay? The steady state error for a unit ramp is, we're going to apply a unit ramp here, and the steady state error is equal to B over Kp for a unit ramp 1 over S squared. And since the characteristic equation, observe the characteristic equation, which is the denominator of this equation here. The characteristic equation is Js squared plus B plus Kd times S plus Kp equal to 0. The effective damping coefficient is B plus Kd. This is the effective damping coefficient, and the damping ratio zeta is the damping ratio is B plus KD divided by 2 times KPJ. This is the damping ratio. Therefore, it is possible to decrease the steady state error and the maximum overshoot by making B small and Kp and Kd large. Okay? One more time. It is possible to reduce as much as possible the maximum overshoot and the steady state error by making B small and Kp and Kd large, so that the damping ratio will be between 0.4 and 0.7. Okay, my friends, this is the theory. Now let's implement a PID controller using 2 operational amplifiers, 2 capacitors and 4 resistors. Now let's implement an electronic PID controller. Observe the figure of the board. The PID controller has 2 operational amplifiers, 2 capacitors, and 4 resistors. Observe that Z1 is the parallel connection. Z1 of S is the parallel connection between resistor R1 and capacitor C1. Observe that the resistor is represented by its resistance and the capacitor represented by its reactance in the complex domain. And observe also that Z2 is the series connection between the resistor R2 and the capacitor C2. That is Z2 of S is equal to R2 plus 1 over S C2. If Z2 of S over Z1 of S is R2 C2 S plus 1 over C2S times R1 C1 S plus 1 over R1, the global transfer function relating the output with the input will be E0 of S over EI of S will be equal to R2 R4 over R1 R3 multiplying R1 C1 plus R2 C2 divided by R2 C2 plus 1 over R2 C2S plus R1 C1S. Okay? This is the transfer function relating the output with the input in the complex domain. Now we are going to rewrite it in accordance with what we studied before this step. We are going to rewrite to observe the proportional gain, the integral gain, and the derivative gain in action. Let's go. we can rewrite this as follows. Is 0 of S over E I of S is equal to R4 multiplying R1 C1 plus R2 C2 divided by R1 R3 C2, and this multiplies 1 plus 1 over R1 C1 plus R2 C2S plus R1 C1 R2 C2S divided by R1 C1 plus R2 C2. Okay? When this is written in this way, we can say that is 0 of S over EI of S is equal to Kp multiplying 1 plus Ti over S plus Td times S. Notice that the second operational amplifier, this acts both as a sine inverter as well as a gain adjuster, okay? Because we have here R4 divided by R3. We can use this ratio between R4 and R3 here to adjust the gain Kp. The proportional gain Kp can be adjusted by adjusting the ratio between R4 and R3. Okay? And what is Kp? Kp is the proportional gain. What is Ti? Ti, as we saw, is the integral time, and Td is the derivative time. This is one way of expressing the transfer function of the controller. There is another way, an alternative way. I'm going to show you now. An alternative way is to write it in this fashion. Okay? Now we are observing the gains, and Kp again is the proportional gain. Ki is the integral gain, and Kd is the derivative gain. Okay, my friends, this is all for PID controllers. This is the theory. Now we are going to solve 3 exercises to practice and see the theory working. Let's go. Exercise 1. What is the steady state error the closed loop control system presents when subjected to a unit step input? This is the question. Let's go to the solution. Observe that we want to calculate the steady state error of this closed loop control system when it is subjected to a unit step input. Let's go to the solution. The steady state error, by definition, is given by okay? The steady state error is equal to the limit when s goes to 0 of s times E of s, where E of s is the actuating error signal expressed in the complex domain. From the block diagram on the board, we can infer that E of s is equal to R of s minus Y of s. Okay? The error is equal to the reference input minus the output. Okay? The output Y of s can be expressed as Y of s can be expressed as R of s minus Y of s. You can check it. 3 over s. Okay? Here, 3 over s. R of s minus Y of s. Minus R of s multiplied by 2 over s plus 2. Okay? This is the expression for the output, which, after some algebraic manipulations, becomes, we are going to reduce this, simplify this into this. Y of s is equal to R of s 6 minus 2s over s squared plus 2s plus 6. Okay? Substituting this here, we observe that the error signal E of s is equal to R of s multiplying s squared plus 4 times s divided by s squared plus 2s plus 6. Okay? This is how we correlate the error signal with the reference input. And knowing that for a unit step input, R of s is equal to 1 over s, we are going to substitute this here and use this expression to calculate the steady state error. Therefore, the steady state error ESS is equal to the limit when s goes to 0 of s 1 over s multiplying s squared plus 4s over s squared plus 2s plus 6, and this is equal to 0. Why? Why the steady state error is equal to 0? If you comprehended what we learned from the video, you're going to discover that this happened because of the integrator. Observe here. There is an integrator there. One of the main purposes of using an integrator is to reduce the steady state error to 0. Okay? Therefore, the steady state error is 0, and this is the solution of exercise 1. Now let's go to exercise 2. Exercise 2, the open loop transfer function of a DC motor is given by W of S over VA of S equal to 10 divided by 1 plus 10S. When connected in a feedback loop, as shown by the figure, what is the value of Ka, the proportional gain, that will reduce the time constant of the closed loop system by 100 compared to the time constant of the open loop system? This is the question. Now let's go to the solution. For the open loop system, W of S over R of S is equal to 10 over 1 plus 10S, which is equal to 10, 1 plus tau S, where tau is equal to 10. Okay? We want to reduce this by 100. This is what the exercise wants us to reduce the closed loop system by 100. The time constant of the closed loop system by 100 compared to the time constant of the open loop system. For the closed loop system, now the closed loop system, W of S over R of S is equal to 10 Ka divided by 1 plus 10S over 1 plus 10 Ka over 1 plus 10S, which is equal to 10 Ka divided by 1 plus 10 Ka plus 10S. If we divide both the numerator and the denominator by 1 plus 10 Ka, we get this. We are going to divide by 1 plus 10 Ka, we get 10 Ka divided by 1 plus 10 Ka divided by 1 plus 10S over 1 plus 10 Ka. Okay? And according to the question, 10S over 1 plus 10 Ka has to be equal to 10S divided by 100. Okay? This is, okay, what we have to divide by 100. This is the time constant of the closed loop system. And if we conduct some algebraic manipulations here, we're going to discover that Ka is equal to 9.9. Okay? By dividing 10, the open loop time constant, by 100, firstly we got this. Okay? Observe that the time constant is the number that multiplies S here. Okay? This, okay? we conducted some manipulations here and we discovered this. Here 10 multiplies s. Here all this multiplies s. Then this has to be equal to this divided by 100. This is what we did, and we discovered the value of the proportional gain as 9.9. And with this value, we satisfy the problem. We completely solve it, okay? This is everything for exercise 2. Now let's go to the last exercise 3. Now let's go to the last exercise. Exercise 3 says, consider the control system shown by the figure, which is subjected to a unit step input. The system is stable and has the following parameters. Kp is equal to 4, Ki is equal to 10, W is 500, and zeta is 0.7. The question: what is the steady state value of Z? This is what we want to calculate. The steady state value of Z. Okay, my friends, this is the question. Let's go to the solution. For a unit step input, R of S is equal to 1 over S. G of S is going to be equal to Kp, the proportional controller, plus Ki over S, the integral controller. They are combined here. This is a PI controller, a proportional plus integral controller, multiplying this, which is the plant. Okay? And since the transfer function of the feedback element is equal to 1, H of S equal to 1, the closed loop transfer function of this block diagram is C of S over R of S equal to G of S, 1 plus G of S, H of S, which is G of S over 1 plus G of S. And since the error signal is the error signal here, is R of S minus C of S. E of S is going to be equal to R of S minus R of S. G of S over 1 plus G of S. And then we find that this is equal to R of S over 1 plus G of S. Okay? This is the simplification of the expression of the error signal. Therefore, the steady state value of z is z steady state is going to be equal to the limit of s going to 0 as z of s and then z steady state is equal to the limit s going to 0 of s times ki over s times 1 over s 1 plus kp ki over s w squared s squared plus 2c 2 times s 2 times w times s plus w squared, and this gets reduced to this. Z steady state is equal to ki divided by ki w squared over w squared, and this is equal to 1. Okay? The conclusion is that the steady state value of z is equal to 1. Alright. Okay, my friends, this is the video that I wanted to make covering the topic of proportional plus integral plus derivative control. I hope you enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!